Okay, so we're going to carry on talking about the inorganic chemistry, section 2.3, the reactions with the halogens, group 7. Okay, now if you've not looked at redox for a while, and this here 1.7 redox, if you want to have a look at that, so there's a playlist on this channel for redox for section 1.7, or look in your book, whatever. But you need to be fairly okay talking about how to assign oxidation number. You need to be able to do that and be all right about oxidation number, writing half equations. Yeah, you want to be fairly au fait with all that stuff. Right. So now in the last video, we looked at we said the halogens themselves in red here, they're oxidizing agents because they're pretty good at grabbing hold of electrons. Fluorine is very good at oxidizing. Chlorine is a very good oxidizing agent as well. Fluorine is obviously the best. By the time we get to iodine, it's not that brilliant at being an oxidizing agent. And of course, the converse of that is that these things, the blue things, the halide ions, these are all potential reducing agents. Iodide is an okay reducing agent. Okay, it's the best one. It's the best one out of the lot, but it's not a brilliant reducing agent. It's just okay. It's an okay reducing agent. Bromide ion is not really very good at all. It is okay, and chloride ion is a poor reducing agent. It doesn't really reduce things at all. And fluoride ion would be about the worst reducing agent you can think of. It's got no tendency to give away its electrons. So what we want to do, we want to show, and the exam board are pretty keen on you doing this. They want you to show, let's just highlight these reducing agents here, and they want you to show that there is the increasing strength as reducing agents. Now, how can you show if something's a reducing agent? You can react it with something that will, so it wants to give away electrons, these things, don't they? They want to give them away. And so you need something which accepts electrons. What accepts electrons? What kind of things do that? Well, oxidizing agents. So what you need is to react these with oxidizing agents to demonstrate that iodide is the best one. Now, if we did this, if we reacted with a strong oxidizing agent, that wouldn't show us anything at all, because a strong oxidizing agent could take electrons off all of those things, okay, like hydrogen peroxide or something. So we're not going to do that. So what we want is we want to demonstrate this trend by using a weak oxidizing agent. So we want to demonstrate this trend here by reacting with a weak oxidizing agent. And that weak oxidizing agent we're going to use is something you wouldn't think of it as being an oxidizing agent at all, but it's concentrated H2SO4, concentrated sulfuric acid. Right, now the reason why it is an oxidizing agent is because if you look at I've got a little ladder here, the oxidation number of sulfur in sulfuric acid is, to do that, the oxidation of sulfur in sulfuric acid is +6. So it has this tendency to drop down. Okay, so as its oxidation number goes lower, it's getting reduced. Okay, so what the experiments that the exam board want you to do, and it's quite a nice set of experiments and quite a confusing set of experiments actually, people always do get a bit confused by this, is you usually do it on a watch glass, and you get some solid potassium halide. Okay, so solid KCl or KBr or Ki. You wouldn't do it with solid KF because that would give off poisonous fumes of HF, and you wouldn't want to do that. So, but you get these, and what you do is you get a little, so you got them on a watch glass, And here is a pipette, my little pipette, which I'm very good at drawing sometimes. Okay, with a nice little, okay, that's all right, that's not bad. Okay, and what you've got in here, you've got some concentrated sulfuric acid, which is an oily liquid, and you drop it onto there, okay? And you get a reaction occurring because, in some cases, because this is it's a weak oxidizing agent, and you get various fumes of gases and things coming off here, and that tells us what's going on. Okay, let's just think, what color are all these things? These are all white, nice white solids. Don't think the potassium iodide is brown and more purple or anything. It's not. They're all nice white solids, look like salt, like sodium chloride. Okay, so what happens here when we react these is we get redox reactions. Okay, I'm going to try and move that picture out of the way. I don't want to rub it out because I think it's nice. That didn't work. Okay, try again. It doesn't work. I'm going to bin it. Right, let's move it down out of the way. Yeah, that's gone. Good. Right, so right, let's think about what our halogens can do here. Okay, or halide ions, sorry. So I'm only really interested in this bit. I'm going to get rid of all that stuff now. Right, so right, okay, so I've got my sulfuric acid, conc sulfuric, and as we've said, we halogens can do a bit of reducing there. Okay, so we get our very worst halide ion, the chloride ion. Fluoride is even worse, that won't do anything. And can it reduce the sulfuric acid from +6? No, it can't. It can't do anything. So we put so if you add KCl plus conc sulfuric acid, you do get a reaction, but there's no redox occurring. The chloride ion cannot reduce the sulfuric acid. You put the bromide ion, you do get a redox reaction. It can reduce, the bromide can reduce it down to SO2. And so if you add some KBr and conc sulfuric, you'll get this choking smell of SO2. Usually described as choking. You're supposed to do it in a fume cupboard, so you shouldn't get the choking smell. Right. Also, if you're going to get this SO2, because the bromide is getting is reducing the sulfuric down to there, so that means the bromide itself must be getting oxidized, and the bromide does get oxidized. It gets oxidized to bromine vapor. So you're going to see some nice brown fumes. So when you added your conc sulfuric to your nice white virginal white KBr, and then when you add that to it, it goes into this dirty brown mess because you're making bromine, and you get these SO2 choking fumes coming off it. So that's what happens with KBr. Let's see what's going to happen with iodide. Okay, so I'm going to add some iodide there. And iodide is a better reducing agent than bromide, and it can reduce it to SO2, so you get some choking fumes of that. But it can also reduce it even more down to sulfur, which is a yellow solid. So you get a bit of yellow solid on your Petri dish, on your watch glass, sorry. And also it will reduce it down to there to H2S, which smells of rotten eggs. So I'm going to do that in a different color. Okay, so let's do the Ki plus conc sulfuric acid. You see a few things going on there. Right, you get SO2, gas, choking, smell. If you do it out of a fume cupboard, you'll notice that. I usually do it out of the fume cupboard, just so you can smell it without poisoning everybody. Just use a very small amount. You will also get some sulfur, which is a solid, so you'll see a yellow solid on the dish. You get some H2S, and if you remember what that's a gas that smells of rotten eggs, and it's a very potent smell. And people standing near to us, people standing in the back, sort of a few meters away, will say, "Well, I can't smell anything." Whilst the people at the front are going, "Ugh, horrible rotten egg smell." And of course, right, if our iodide is doing reducing itself, it must get oxidized. What's it get oxidized to? It gets oxidized to I2. So you get some I2, and generally, because it gets quite hot, you see that as purple vapor. And you'll also see a bit of black solid on the dish. That's solid iodine. You see, so you get a whole, you get your white, the nice white potassium iodide. Okay, as I said, it's lovely white, it's like pure, clean salt, and it ends up like a dirty mess. You get some black solid on the dish. You'll end up with some yellow solid on the dish. You'll get rotten egg smell. You get all kinds of nasty vapors coming off that. Okay, that's what happens with Ki. Right, we need to talk about what happens with KCl. Okay, because I said there isn't a redox reaction there, but we do see something with KCl. With KCl, I'll do it in black. You get steamy fumes of HCl. These are always called steamy fumes. Okay, I think it's because HCl is very soluble in water, so what it does, it dissolves in a bit of water vapor in the atmosphere, and you get little clouds of hydrochloric acid forming. Okay, steamy fumes of HCl, and that is not a redox reaction, because let's see what happens. You get KCl, and you react that with sulfuric acid, and you get HCl, and you get potassium hydrogen sulfate. Okay, now let's see what's happened there. Let's try and work out what has happened. Okay, now we look at the oxidation numbers. Chlorine here has got a -1 oxidation number, and chlorine here in HCl, that's got a -1 because the hydrogen is always +1. So no change in oxidation number. It's not a redox reaction. Well, what kind of reaction is it? Well, the Cl- has gained an H+ to form HCl, covalent HCl. So what's it called when something gains an H+? When something gives away an H+, that's an acid acting as an acid. So the LCl- has acted as a base in this reaction, and the sulfuric acid has acted as an acid, not as an oxidizing agent. It's given away an H+ ion. So I think it's going to make this video a little bit long, but I think we need to write down those equations now. You can maybe have a little break and pause it and go away and do something or whatever, or just decide not to watch the rest of it because it's too boring. But let's have a quick look at let's see those reactions. Okay, we're going to have to write half equations. Right, let's do the the potassium iodide first of all. Okay, so the Ki plus concentrated sulfuric acid. Right, we've established there that what happens is the iodide gets oxidized to iodine. So let's write a half equation. So we've got to balance the elements of interest. So we want 2I-, and here on this side we're going to make we're going to get 2 electrons, balance the charges. So that is the I- is oxidized, and it does a little bit of reducing. The I- reduces things. So what does it do? It reduces sulfuric acid, H2SO4. Let's do the first reduction, which is all the way down to H2S, smelly rotten egg smell. Right, got to balance for the oxygens first, so we're going to put in four H2Os there. Balance for the hydrogens, so we need 8H plus there. Balance for the charges, and we're going to have 8E minus there. Okay. So if you wanted to write a full equation for what's happening, you could combine these two together. You would have to multiply this one by 4, wouldn't you? And you could combine them together and write a full equation. We won't do that. Or you could just have it going, the H2SO4 going to sulfur, not being reduced quite as much, only going down to sulfur, which is a 0 oxidation state. So let's do the same again. Balance, we need 4H2O on this side. We're going to need just 6H plus here. And we're going to need 6E minus to balance the charges. So if you wanted to combine that and that, you'd have to multiply this one by 3 this time. Right, alternatively, you could have the sulfuric acid only getting reduced to SO2. So that means you just need 2 waters there. That means you need 4H plus there. Sorry, 2H plus. And you'd only need 2 electrons, which would of course be coming from the iodine. So if you wanted to write a balanced equation for these two, yeah, you wouldn't have to do any multiplying because that wants 2 electrons and that wants 2 electrons. Just add them together. Right. So, right, let's do it for the bromine one. For bromine, so KBr plus H2SO4. Should draw a line under that, separate it. Okay. Now that one, what's going to happen there? Well, the bromine gets reduced, doesn't it? So it's going to be very similar to the iodine. You're just going to get Br minus, sorry, the bromine gets oxidized. It goes to Br2. So we need to put a 2 there. Balance of the charges, you need 2 electrons there. And we've said that bromine could only make the SO2. So it's this equation here. So I won't write it out again, but I kind of will write it out again just to make it easy. So I've got a record, I've written it. So H2SO4 can only get reduced to SO2 by bromine. It's by bromidine. It's not such a good reducer as iodine. You can only get it down to the +4 oxidation state there. Remember, you're going to get right. We are going to need 2 H2O there. So that means we need 2H plus, and we need 2 electrons. And combine those two to just add them together, and you will get for the balanced equation. So now with the KCl, I said you don't get any redox, so can't write redox equations. You only get the acid-base reactions there. So I'm going to do a little summary table of the products that you get. Okay, so this is when you add. So you're adding, let's say, with KCl, with KBr, and with Ki, all solids. And this is when you react them with concentrated sulfuric acid. So you're adding Conc H2SO4. These reactions don't work if you do it with dilute, because the concentration of the reactants is too low and you don't notice a reaction occurring. So we're doing that. Right, and so I'm going to write down the products that you get with each of those. Okay, so the products, is the key is going to be, if it's a redox reaction product, I'm going to do it in red. And if it's not a redox reaction, if it's a result of an acid-base reaction, so in other words, exchanging a proton, I'll do that in blue. KCl is the easiest one, it's the simplest one. You're only going to get one product. You will just get HCl. Oops. HCl, what does that look like? HCl, steamy fumes. and you can test for, it turns damp blue litmus, it will turn it to red. Right, so that, I think I can see I'm going to need a bit more room here. Move that down, just move this down just to show us the key. Doesn't want to move down, some strange reason. Okay. Right. Right, KBR then, what do we get there? Now we do get redox products there. We're going to get Br2. The bromide ion is oxidized. That's red fumes. You are going to get SO2. We said it's choking. Smell. And they're the only redox products you get, but you also get the acid-base reaction there. You don't get HCl, you get HBr, and that's steamy fumes. You'll get with that. Ki, this is quite complicated because you get a lot of redox products. You get I2, so that should be done in red because it is a redox product. So the iodide is oxidized to I2. That's purple vapor or black solid. You will get SO2, choking. But it can also, the sulfur can get reduced not just from the +4 to the 0, so you'll get, that's a yellow solid. And you're also going to get H2S, which smells of rotten eggs. And then you will also get, we didn't really come across this, it's HI, which is very similar to HCl and HBr, HI. And that comes as a result of a redox reaction, and you will get, that will be steamy fumes. We should also say what is also, when you form HCl, because you're taking a proton off the sulfuric acid, you're going to get potassium hydrogen sulfate, and you'll also get potassium hydrogen sulfate there. And I'm doing it in blue because it's not a redox product, it's an acid-base product, and you get potassium hydrogen sulfate there as well. Right, that's a very long video, so I'm going to call it a day there. But just to remind you, that is in required practical 4. In the AQA, required practicals, and if you do it, it's tricky to do because you've got to do it in a fume cupboard. If the students are doing it, it's all right for the teacher to poison the students, but not for the students to poison themselves. Okay, so we'll leave that there.